Yeah, thank you for the nice introduction and, of course, the invitation. So I'm really happy to speak here today. I'm going to speak about tiny drones as a showcase for neuromorphic AI. I guess that everybody here knows and hopes and believes that robotics is booming. So I found some numbers on some, you have these economic foresight websites like apparently 7.5 billion in 2024 and 34 billion market for autonomous robots. And a lot of this is powered by AI. So yeah, I'm not telling anything new to you here, but of course, AI is really important and we want these robots to become smarter and more capable. But the problem, of course, is that AI typically is quite heavy and power hungry. I want to illustrate it a little bit with drones. And to be honest, I just want to show this video. But normally, if you think of autonomous drones, then we think of these quadrotors. And what you will see here is two quadrotors. One is powered by AI, so it has our code on it. And the other one is the exact same drone. It was made by an organization in Abu Dhabi of this drone race. And it's controlled by a human. And this was last April, and it was the first real competition between humans and drones, where with a knockout tournament. So if you lose, you're out, and that's it. So let's have a look at how we fared. So the human took off quicker, and then our drone actually overtakes it in the first lap. And it's going quite fast, so around 100 kilometers an hour. And the human got a little bit stressed, so flew into the gate, and we finished the lap. This was the quarterfinal. We did also a semifinal and a final, which you can watch at your own leisure, but in the interest of time, I'm going to continue. So if you look at this drone, which again was made by the organizers, it's here. It's around 700 grams. And in order to run AI on board, they give it Orin NX. So the NVIDIA Jetson Orin NX, it weighs 50 grams. I made it red because I think it's heavy. And why do we need the Orin? Well, mostly for the vision. So we have a pretty big vision network. Well, pretty big. Actually, we made it really small, to fit on the Orin compared to computer vision people, but I would find it big. And that's why we need the Orin. So it's running at 90 hertz, the network. And it's running to detect gates, which we need to do because we need to fly through them. And then we have actually, so why was the drone so fast this time? Because the control was also done by a neural network, but it's really small. That's why you almost don't see it on the slide. And it was actually running on a STM, so a little microcontroller. And this thing was actually going from the state, so where is the drone, to the motor commands directly. This really made it very, very fast. Okay, now why am I saying I find this heavy? Because we in our lab we also work on flapping wing drones, and these are much more lightweight. So what you see flying into this is an insect, but the other one was our drone, and it weighs 29 grams and uses 6 watts to fly. You can imagine that we can simply not put an R and an X on this thing. But I would like these flappers to be intelligent because they can fly in greenhouses. They're super safe for humans. So even if they hit them, then nothing will happen. If you're hit by our racing drone, then you have a big headache or concussion, and I hope you survive, right? But if you're hit by this thing, we actually accidentally hit someone in the face with it, nothing happened. And so that's why we want them to be, intelligent as well. And in order to do so, we actually hope that the promise of neuromorphic AI is going to come true. Now, I guess most people here know this promise very well, so I'm going to be a little bit quick about it. So, why does it promise to be very efficient? Because it mimics animals' asynchronous and sparse sensing and processing, which can save you a lot of energy, but also makes the brain and the way we sense much quicker. Now, you've seen many illustrations of this, but if you look at this event cam here, if you look at the normal camera filming the propeller, it's totally blurred because the propeller turns very fast. On the event cam, you can see it very well. And then what we are interested in is to process these things now with spiking neural networks on neuromorphic processors. So what is the state of the art with these spiking nets? I'm not the main expert on SNNs in the world, I would say so, but from our experience, if you do supervised learning, You typically use backprop in normal ANNs. At the start of the SNN field, this was very hard to use because the spiking function is the heavy side, which basically is not differentiable. And so the solution they found is actually pretty simple. It's to say, okay, when we propagate spikes through the network, we use the heavy side. But when we do backprop, we assume it's actually not a heavy side, but a sigmoid. And so basically, you assume in the backward pass that you have a continuous function, and this works quite well. So training is still harder, especially for deeper networks, because of the dynamics. So the neurons also have a leak. It's like the membrane voltage in your neurons. And this means that sometimes a layer dies out and then learning stops. So training is still more difficult. And if you succeed, the accuracy is slightly less. Am I selling it well, the spiking neural networks? So, but of course, we hope that they're faster and more energy efficient. Okay, so neuromorphic AI in robotics. So we've seen some very nice examples in the first talk. So I think there's more and more examples, but why is it not mainstream yet? Well, in my eyes, because well, one, SNNs are harder to train still, and the sensing and processing. Yeah, I hope I don't insult anyone, but it's relatively immature compared to, super immature CMOS and whatever. I'm super happy to see that we have products now, and I think that in a few years, we will really reap the benefits. But as a roboticist, like, yeah, Andreas was also saying this, like, yeah, you're like, I don't know much about hardware. I just want to do my stuff. Well, if you do, it's not, yeah, I mean, there are not many neuromorphic chips that you can simply buy. Documentation is typically okay-ish sometimes, challenging, and the network sizes are relatively limited compared to what you can do on traditional hardware. Uh, I have a clock here, but I forgot to press play, so that's nice. And so let's talk a little bit about very limited network sizes. And so this is, if a biologist would be here, they would kill me, but okay. And so if you look at the number of neurons, then we as humans have 86 billion neurons. And ChatGPT was actually slightly smaller, three. But I think four and five, they're beyond the human scale. And then if you look at neuromorphic chips, and these are rough estimates, let's say, because it all depends on details. But you have this Rolls chip, it's like a few hundred. Intel Capoe Bay, they were saying 1 million, but let's say a few 100,000. Sinsen Spec, Spinnaker, they're in a very different range, right? So you could feel depressed about this, but you could also think like, hey, there's other animals than humans. And so and then you're looking there. To be very honest, Rolls, yeah, it's a cool chip, of course, but yeah, the worm is a very useful animal. But as a roboticist, you typically want to do a little bit more. But if you then look at insects, they actually are very intelligent creatures that can do, yeah, super cool things actually already, like navigate for 10 kilometers and come back. They take group decisions. They learn from each other. It's really awesome. And if you look at their number of neurons, it's actually in the range of these chips at the moment. And obviously, these chips are going to advance. So I think, like, yeah, if we focus a bit on that kind of intelligence, then we may be able to really show super cool autonomous things with even small robots. Now, I put a spec in here, of course, but because yeah, I think that's very promising. This is basically what we want. Of course, we would like the chips to get the capabilities to increase perhaps a bit towards the future, but this is something you can buy. It's actually not very expensive, and it already has a 9-layer convolutional network on there, but it has around 320,000 neurons, which is basically the number of neurons of like an ant, that can do already, very, very many things. So here we go from the promise to something even more ethereal. So what is my dream? And so my dream, it doesn't sound, I mean, most people don't dream of this, I guess, but would be to implement an entire autonomy stack on a single neuromorphic chip. I think it is a dream that's kind of shared between neuromorphs. So it's not only my dream, I guess, but I work on drones. So what it means for me is that we have preferably event-based sensors, and they feed into a spiking net. It will probably be modular, not like one Moloch of a spiking net, and then basically it will send commands to the actuators. And I wanted to do all kinds of things. So what do I mean with a full autonomy stack? So on a drone, you need attitude control, ego motion control, obstacle avoidance, navigation, and yeah, with robotics, of course, we need to do also an application. So that it actually does something people are interested in. That's also nice. And so today I will talk about these first two levels because we actually did quite some work on that over the years, and yeah, I want to communicate what we found. I'll start with ego motion control because that's actually the thing we started with, and it feeds into the attitude control later. Oh, I don't know. Oh, there's like animation. So, like, yeah, these are some work. So, I used to work on optical flow control on a normal drone with a normal processor. And so, I had a normal camera and it fed into a traditional vision pipeline, which I made red outlines. So, because we don't want that, obviously. And I was doing things like optical flow landing or obstacle avoidance, things like that. Then we started to work with event cams and bringing them into the control loop for the first time on a drone. Then we said, okay, yeah, but the processing is still, yeah, kind of traditional with algorithms and running on, traditional chips. So a very early study we did, which I really liked, was that we went from events to even global flow, like basically ego motion, with a spiking neural network, which at that time was a huge challenge. And we even used local learning for it. So basically, it was fed events, and then you had these neurons learning on the fly, how to extract features, local flow, and global flow fields. But I made it orange because it never ran on any kind of chip, and actually it used delays on the connections. So that's still something you would not be able to find a chip for now. So later we went to a design that was more compatible with current chips, in which we use self-supervised learning for optical flow. But I made it light green because we never ran it on a chip. It was still slightly too large. And then we actually, for the first time, did control with a neuromorphic processor. And for that, we used the Intel Loihi. Now, I'm not going to talk too much. That was like 9 years of work. But and what I'm going to present is something we published last year in Science Robotics. So we had an event cam going into a spiking net, and then this was decoded, the outputs of the network, and those were low-level commands to the drone. And this is a little look into the brain. So yeah, because of the setup of the Loihi, reinforcement learning, then you basically need to simulate these events, which is really a time-taking process. And because you need to do hundreds of thousands of rollouts of your policy, and then you need to simulate these events. And if you want to do it well, you generate 1,000 frames per second. This is just was not possible at the time. If only someone had a solution to that. No one yet? I see one person smiling. Sorry. Okay, and so what we did instead was splitting vision and control. But how do you do that? So what we did is we had an event cam looking down on a drone, by the way. So we're going to look down, and then we see this pattern, and then of course you have the events, and from these events we entered those into a spiking net, and it would output the optic flow of those four corners. And if you look at the flat surface, then four flow vectors are enough to encode your ego motion. And so it's, because of the homography, but anyway. And then what we did is separately, because if you know the motion of your drone in simulation, which is a physical thing, you can transform it to the flow you should see in the four corners. That's just a tiny mathematical transformation. And then we put that into a second spiking net, which we evolved in simulation to send control commands to the drone. And so these are attitude control commands, which is relevant for the second part. But so and what we developed in our science robotics study was a way, if you train two networks and you use encoding, like learned encoding and learned decoding, then you can actually merge these networks together. And so how does it work? So suppose you have spikes in, like we had, and then it goes into the optic flow network. Then it's decoded in the final layer with a matrix. So you have spikes in the final layer. You multiply the spikes by a matrix. It goes to the outputs that you want. In our case, 4 flow vectors, 8 numbers. But these are floating point numbers. This vector I, y is floating point numbers. In the simulator, we had the opposite thing. So we knew the motion of the drone. We transformed that to these 8 floating point numbers, and we entered that into a network with the same kind of encoding. So you take the floating point numbers, you multiply it with a matrix, and this forms the current input to the input layer. And so this is a matrix at the start, and at the end, it's decoded again, also with a matrix to the commands that are sent to the drone. But now our problem is, yeah, we have these two networks and we have floats in between, which you don't want in your chip. Yeah, you cannot have it actually in your chip. And so how do we get rid of this floating point vector y? Took us half a year, and then we were very ashamed that the solution is super simple, because the decoding is with a matrix, the encoding is with a matrix, yeah, and two matrices multiplied together is actually also a matrix. And so if you do that, then you can actually merge these two networks, and you have spikes all throughout the merged network. And so we learn the vision with self-supervised learning. I'm not going into details in the interest of time. But the cool thing is you just gather data with your event cam and then it learns. So you don't need ground truth, you need nothing. And actually, the network is trained for your specific camera. So if your camera is a bit weird, then yeah, it still works. And so that's very nice. This was a training procedure. So for the control, so we trained a simulation. And then we deployed it in the real world. And this is what the hardware setup looked like. I think for roboticists, this is relevant. So the Loihi has, so it was a Loihi 1, Capo Bay. It has a connection to a DVS camera, but it was a very specific model that they were no longer selling. So we didn't have that. So we had to connect the Loihi to an up squared board and an up squared board to the camera. And that's why we had very limited bandwidth between the camera and the Loihi. So that's why we went for these 4 corners, but it still worked. And I'm going to show you a video of that. So on the left, you see what the drone sees, and on the right, you see the activity. You see the drone moving forward. It's looking down, so if it's going forward, then all these events are going to the back. And basically, we can give any command. So go forward, go faster. And so here we make it go faster, and you see that the events go back faster. And this is the kind of pattern that you also see in the neural network. We could also land, and the cool thing of event cams is that this also works yeah, in relatively dark conditions. So why are we doing this? So I'm a little bit in between. I care about the biology, but to be honest, like, yeah, I also want to make sure, like, yeah, does this then actually give us benefits, right? So, and it's actually pretty hard to find numbers in the literature. Like, yeah, it's just hard. So we really just measured. So we had an NVIDIA Jetson Nano. We implemented the same network on there, but we didn't make it spiking. So we did a floating point because yeah, if you have a GPU, you're not going to put a spiking network on there because it's actually slower and worse. So why would you do that? And so we put the floating point version on there, and we put the spiking version on the Loihi. And if you look at the frequency, then the Loihi was much faster, so 10 times faster. And the 274 hertz is when you have many events. So you move fast, a lot of texture. But if you have fewer events, then you can also yeah, hit the 1600 hertz. So it's really, really fast. In terms of energy, that's also interesting. So there's 2 numbers there. The first number is the idle power. So on the NVIDIA Jetson, you have a 1 watt idle power. On the Loihi, we have a 0.9 watt idle power. So that's huge. And yeah, talking to Loihi, yeah, to Intel, they say, yeah, we can cut that down. But if you look at the power that is necessary for running the network, then it's like almost 2 watts for the Nano, and it's like 0.007. So it's like 7 milliwatts for the Loihi. And I think there, you can see the promise of this technology. But if we just take the current numbers, then it's already, more than 10 times faster and more than 3 times more energy efficient. And so that's already, actually quite a good factor, I would say. So yeah, I think the promise is going to happen. I have the time here. Oh, good. Yeah. So attitude estimation and control. So what I said was, yeah, this pipeline went from vision to attitude commands. But if you want everything on the neuromorphic chip, also the attitude control has to be on the chip. And this is actually something we presented here at IROS this week. So we have this approach where we merge two networks. So we're merging it again in the same way to attitude estimation and control. So we have an attitude estimation network that has a recurrent layer as well, it's spiking, and the control network is also recurrent. We train them with imitation learning, so we use a normal filter for the states, and then we gather a data set, and the normal filter is the targets, and the spiking net tries to mimic those. That works actually pretty well. If you make a varied data set, then the training works very well. For the control, we had to do more tweaks. So we actually tried to mimic a PID controller with the control network, and that was quite challenging. The P term is no problem. The D term is already challenging, and the I term, so D is the derivative, I is the integrator. This is actually challenging with a spiking net. So what we did is that, yeah, one challenge with imitation learning is that, yeah, you learn on a data set, but then you run the network and it behaves differently from the PID controller. And then basically, yeah, you get a data distribution shift. That's why what we did is we gathered data, we trained, we deployed the spiking net, gathered more data. We also did disturbances in flight to get a varied data set. Another thing was that the spiking net was predicting the attitude or estimating the attitude with some delay. So what we did then in our training was, okay, let's make it predict not the attitude at this time step, but a few time steps in the future. If you do that, it actually almost removes the delay. So it was very nice. And the integrators, if you leave the parameters of we had leaky integrate and fire neurons. If you leave the parameters free, then actually the network doesn't learn to integrate. So we actually, it's a bit following the AI literature. They also do special tricks to make sure that the recurrent layers don't blow up or die out. And what we did is we fixed the leaks for some of the neurons, and then we did learn the weights, and then it could learn the integrator. So we did these tests. So this is, control people love this. So you have the black lines are the reference points, and then the blue lines are 10 different flights with our spiking net. So you see it works. On the bottom right, you see the PID. So even after all our tweaks, the blue one is a little bit more oscillatory. So as an experienced drone pilot, you see it. But the error actually was very similar to the PID. And so it works. And for me, that's enough. So here, basically, I show, so this is actually 4 years of research by one of the PhDs, Stijn Stroobans. And then we were like, oh yeah, so after 4 years, we're slightly worse than a PID. So don't tell to Stein that I said this to you. But like I showed at the beginning, we're doing this drone racing, and there we're using these neural networks. So we're now working to spiking nets that do this. And we actually had our first result, and we're going to show this at IMAV in a week or so. And this is a drone that's being controlled by a spiking neural network. Let me see if I need to click, I guess. Yeah. Yeah, so I cut the sound. Very good. Yeah, with the sound is also impressive, but this is not a spiking net, so this is normal control. But when the drone, this is the spiking net. And so it's flying in H shape, and basically, it's really, perhaps with the sound is more impressive, but it's really the same performance as we get on the racing drone you see at the start. And so it's really very, very fast. The spiking net is still a little bit special, like we're doing a trick that I don't like, but so we run inputs and then we reset the network and run the next input. So that's ugly, okay, but it's the first step, and I'm pretty confident we will get there to do really high performance control. Oh, it's flying again. And so to do really high performance control with these spiking nets. I think I'm almost there. Yeah, conclusion. So yeah, I think that well, neuromorphic AI is definitely necessary for all robots. Like even the bigger ones, they're limited, right? They're limited in energy they can carry. You want them to be smarter, so yeah. If you only want to do walking, okay, but if you want to avoid and you want to talk to people and more and more bigger networks, so we need to be efficient. This is not only a problem from the drones, but I think the drones are very nice to show this technology because we know that these drones are severely restricted. Uh, yeah, and then okay, what about these other little tasks like so obstacle avoidance, navigation? So we're working on it. There's one poster by Ilun on yeah, that's presenting some first step into the obstacle avoidance. Not perfect yet, but very nice step. And I want to thank, yeah, of course, I did most of this work purely by myself, but I also want to thank a few other people that gave some advice here or there or program. No, so yeah, this is really thanks to many, many people. And yeah, so thank you. And I think that's it from me. Yeah.
Thanks very much. Very nice talk and very professional, leaving time for question as well. Thanks. So, do we have any questions?
Thank you, Professor, for your wonderful talk. Yeah, I have many questions. I just ask two questions. So the first one, when the tiny robots or micro robots or tool is a very good platform to demonstrate the advantages of neuromorphic AI. I think so. Yeah. So how to build a more energy efficient neuromorphic AI by getting inspiration from insects' brain. From the neural circuit level. Yeah, it's the first question. The second question is how to build a unified spiking network model that can implement multi types of functions such as control, obstacle avoidance, navigation, and other tasks together or parallel. Yeah.
Yeah.
Okay, thank you.
Thanks for those questions. So the first question, like, oh yeah, the instance. Yeah, oh, I actually deleted a few slides. That's actually a pity because on the one hand, there's like the advantage you get from neuromorphic processing, which, I think a modest estimate would be 10 times, but I think 100 times could be perhaps achievable. With insects, you can also get like, for example, yeah, there was already the localization that Tobias Fischer is doing with his group. Yeah, some of the people here, they actually work on localization. And just for that task, by looking at how natural intelligence works, they also reduce network sizes by a factor 100 or something. So, and then the cool thing is if you have 100 times smaller network, and this network is 100 times more efficient per neuron, let's say, then you get a factor 10,000. So this is what I'm hoping for. So 10,000 times, it's a bold statement, but yeah, 10,000 times more efficiency because of that. Yeah.
Thank you.
Oh yeah, and the second question, I don't remember the second. That's why.
How do you build the full?
Oh yeah, the full thing. Yeah. So on the one hand, the merging of networks that we found is a way to kind of combine them. But what I think is interesting, so because we want to put everything on a neuromorphic chip, we need to do everything neurally. And I think there's also something with ANNs that, yeah, people, they call it end-to-end there, but it's not solved, right? So it's very interesting challenges. So some of the stuff you may need to do is also arbitrate between different behaviors. And it's like, how do you do a finite state machine in spiking nets? This is something that Julia, for example, worked on in the past, but we have to solve all of these problems now in the spiking net. So I don't have the answer yet, but I just, yeah, I like the challenge. Yeah.
Okay, thank you very much.
Thank you, Professor, for your very interesting and intriguing talk. I also have a lot of questions, but I will only ask one here. I know that there is a new technique called the AN to SNN conversion. I'm curious about, since you also train the ANN models, have you tried directly converting them versus training an SNN from scratch and compare their performance?
Yeah, so there is ANN to SNN conversion. There's different ways of doing this. Some of them I don't like. So, for example, some people, yeah, don't, I don't know if they're here, but like they take a grayscale image and then they encode it with rate encoding and then a spiking net, and then it takes a very long time to classify one image. And then, yeah, that you can convert, but then you get actually something that spikes a lot, and yeah, we need sparseness. So then there's conversion. Yeah, it depends on the neural model. So if you have an integrated fire model, like on the Synsense spec, then you can actually convert it. So if you have a model for which conversion is possible, then I think, and you don't lose like energy efficiency with that, then I think it's a good idea. But in most cases, I don't think it's a good idea because we don't know how to convert them well and retain sparsity, in the computation. Yeah.
You have a question, Julia?
Yeah, I use my own microphone. Thank you so much for the talk. I will bother you later. Just know that. So the first question is, why SNN? Like, I want to understand, what do you do with the neural dynamics? Like, you said that you're using a lift.
Yeah, most of them.
Why? Why do you use the neural dynamics? So, like, what do you do with the time information and that neural dynamics?
So yeah, we use the LIF because it's one of the most common models. Some people say that because of this, SNNs are well suited for extracting temporal dynamics. I'm not fully convinced yet. Like at the moment and that's why we use that also in the attitude estimation network, and we're doing backpropagation through time because so we need these recurrent connections to actually get that temporal processing. I'm not yet convinced that the spiking net is more suitable than the ANN for temporal processing. The fact that it's asynchronous, because I didn't see evidence for that yet, and I think the main difference, so you also have ANNs or RNNs in that case with leaks, and then you only don't have the spiking function. And the spiking function, in my eyes, makes you lose resolution. So it's not a benefit in my eyes yet. Exactly, yeah. Oh, please.
We have a panel discussion at the end, so maybe So let's get back to that question for the panel. Is it?
Yes.
Okay?
Don't ask him. Don't ask him.
How much do you care about the? No, it's this.
Oh, it's this. This is like sorry.
So how much do you care about embodiment? Like, I do care a lot about how I move my cameras around, and they think that we shouldn't suspend our cameras around. I know a bit radical, but I want to understand if you take into account how you move the cameras around in your.
So we really focus on robots doing tasks. So already for optic flow, some of the theories about insects, I don't know, in the intro they were saying, I learned things about nature. It's, for example, that if you actively control your body, then actually, because with optical flow, they always say it has no scale. But one of the things I showed is that, if you have a body and you act, then you can actually find the scale also with optic flow because it's basically linked through your actions. So I care about embodiment a lot. I think it's really important for the intelligence.
Yeah, that's why.
Okay, okay.
We have time for a very quick question. Do we have anyone from the audience? No, okay, me not that.
Slightly biased question. So I was going to ask how come in which aspects this tech came short that you chose Intel Loihi for this work? I'm guessing it's number of neurons or parameters, the configurability of layers, connection types, which kind of flexibility.
Availability was the reason, because this is pretty old work. Like, I mean, we started it long ago. It was very hard to use it, to be honest. Yes. And so at that time, it was the only neuromorphic chip that we could get our hands on. So now we're also working with the spec, which I really like, as you saw. But it has limitations. Like you said, there's many feature requests. So I would request memory, but like recurrent connections. But so now we have the Loihi 2 in the lab. We have